this video, we go over the ratio test for the series and root test. By the ratio test, let's suppose that L is the ratio of an plus 1 over an. We take the limit of absolute value of this ratio. Now, if L is a constant less than 1, we can conclude that series of an converges. If it is a constant greater than 1, then the series diverges. And if the constant is equals to 1, the ratio test is inconclusive. So we need to use another test. When we use the ratio test, because we take the limit of absolute value of an plus 1 over an instead of the sigma an, so instead of evaluate the sigma an, we are evaluating the sigma absolute value of an. So when the absolute value converge, I can say that the original series converges absolutely. So by using the ratio test, actually we can evaluate if a series converges absolutely or diverge. Another test is root test. It's the condition is pretty similar to the ratio test, but for the root test, we evaluate the limit of root n of absolute value of an. And in this case, again, we are evaluating absolute value of an instead of an instead. Okay, if the constant is less than 1, then the series converges and converges absolutely. If the answer is greater than 1, then the series diverges, and again, if it's equals to 1, this test also is inconclusive. Now let's see some examples on root and ratio test. The first example is series of negative 1 to power n, 3 to power n plus 1 over n plus 3 factorial. When in the series we have factorial term, it is better to use ratio test. So let's apply ratio test. By the ratio test, we have an. Here an is negative 1 to power n, 3 to power n plus 1 over n plus 3 factorial. More than an, we need a n plus 1 as well. So let's make a n plus 1. It's negative 1 to power n plus 1, 3 to power n plus 1, and denominator is n plus 1 plus 3 factorial. And then we need to take the limit of absolute value an plus 1 divided by an when n approaches infinity. So the limit of negative 1 to power n plus 1, 3 to power n plus 2 over n plus 4 factorial in the numerator as an plus 1, and an is negative 1 to power n, 3 to power n plus 1 denominator is n plus 3 factorial. Okay, and n approaches infinity. We have absolute value of this division. So I can simplify inside the absolute value and write it as a limit when n approaches infinity, the new fraction. Let's keep the numerator as -1 to power n plus 1, 3 to power n plus 2, and multiply numerator by the reciprocal of denominator. If I multiply numerator, which is this fraction, by the reciprocal of denominator, then the answer is this fraction. Now let's simplify. In the numerator, we have -1 to power n plus 1, which is -1 to power n times -1. We can cancel -1 to power n with -1 to power n, divide numerator and denominator by -1 to power n. And again, in the numerator, we have 3 to power n plus 2, which is n plus 1 plus 1, right? So it's 3 to power n plus 1 times 3 to power 1. And now we can cancel these two. Also, n plus 4 factorial is n plus 4 times n plus 3 factorial. And then we can cancel n plus 3 factorial from numerator and denominator, which is equals to this fraction. And now I can have absolute value of -1, absolute value of 3, and absolute value of n plus 4, limit of these things. Limit of absolute value of -1 is just positive 1, and absolute value of 3 is just 3, and absolute value of n plus 4, it's equals to n plus 4 because n goes to positive infinity and it is positive, so need the absolute value, and it is equals to the limit of 3 divided by n plus 4 when n approaches infinity. Now if we plug infinity, denominator is infinity, and 3 divided by infinity is 0. So you used the the ratio test. You use the ratio test here for this series, and the limit is equals to 0 by the ratio test. If the limit is less than 1, then sigma a n converges and converges absolutely. So this series converges absolutely. The next series is -5 to power n over n to power 28. So which test is better to apply, ratio or root test here? In the numerator, if I rewrite it, you see -1 to power n times 5 to power n, and in the denominator it's n to power 28. So both root and ratio works here. Let's use root test here. By the root test, I'm looking for the limit of root n of absolute value of a n when n approaches infinity. So this is sigma a n. So let's find the limit of root n of absolute value of a n, which is -1 to power n, 5 to power n, and denominator is n to power 28, and approaches infinity. So I can rewrite it as a limit of root n of absolute value of -1 to power n, and also root n of absolute value of 5 to power n divided by root n of absolute value of n to power 28 when n approaches infinity. So what is the answer for each part? Root n of absolute value of -1 to power n, actually it's absolute value of -1, which is +1. So this is +1. Then root n of absolute value of 5 to power n, it's just absolute value of 5, which is 5, right? How about the denominator? Denominator is absolute value of n, actually, under the root n to power 28. Or you may write it as absolute value of n to power 28 divided by n when n approaches infinity. First of all, we do not need absolute value because n is positive. So what is the root n of n to power 28? If you remember from limit of sequences, there was some formulas. If we have a root n of a polynomial with variable n, the answer is equals to 1. So the limit for denominator is 1, numerator here is 1, here is 5. So the answer is 1 times 5 divided by 1. And if you want, and for better explanation, I prefer to write it as limit of root n of n to power 28 and approaches infinity. And in the next step, I write it as 1. And you see the answer is 5. 5 is greater than 1. Do not forget that we are applying the root test here. By the root test, we took the limit of root n of absolute value of an when n approaches infinity. The answer is greater than 1. By the root test, we conclude that sigma an diverges. The next theory is n to power 4 divided by -2 to power n plus 1. For this specific example, you may want to apply root test or a ratio test. Both of these works. So let me apply the root test at the first. By the root test, I'm looking for the limit of root n of absolute value of an when n approaches infinity. So we are taking the limit of root n absolute value of n to power 4 divided by -2 to power n plus 1. Or you may want to rewrite -2 as -1 times 2, and now both has exponent n plus 1. So I can write it as -1 to power n plus 1 times 2 to power n plus 1 when n approaches infinity. And now you can separate them and write it as root n absolute value of n to power 4. Denominator is absolute value of -1 to power n plus 1. Absolute value of 2 to power n plus 1. And you know that it is root n. Okay. Again, you may want to separate them and write it as a limit of numerator when n approaches infinity and limit of denominator, root n of -1 to power n plus 1 and 2 to power n plus 1 when n approaches infinity. Okay, and now just because the exponent here is n plus 1 and I have root n, allow me to rewrite n plus 1 as multiplication of two terms. I want you to see all the steps. So numerator is a limit of root n to power 4 when n approaches infinity, and denominator you are taking the limit of root n -1 to power n times -1 and 2 to power n times 2, and n approaches infinity. Okay, now what we know about the numerator, it's limit of root n, absolute value of n to power 4. N is positive, so you don't need absolute value anymore. And n to power 4, it is a polynomial with variable n. So by the rule, I know limit of root n of polynomial with n, this is equals to 1. So numerator is 1. Sorry, the surface is freezing. Okay. So the limit of numerator is 1. How about denominator? Denominator, you have root n of -1 to power n, and it is equals to absolute value of -1, which is positive 1. And then you have absolute value of -1, which is the positive 1. So the answer for this part is 1. How about this one? We have absolute value of 2 to power n and absolute value of 2. Root n of absolute value of 2 to power n, it's just absolute value of 2, right? And the remaining is root n of 2 when n approaches infinity. So in the denominator, the remaining part is 1, 2, and then root n of 2 when n approaches infinity. Let me write it as limit of root n of 2 when n approaches infinity. And again, by using the rules for the limit of sequences, limit of root n of a, when a is a positive constant, it's equals to 1. So the answer is 1/2 because its denominator is 2 times 1, which is 2. So the answer is 1/2 after you calculating the limit of root n of absolute value of a n. The answer is 1/2. 1/2 is less than 1. So by root test, now you conclude that sigma a n converges absolutely. How about if I want to apply ratio test for the exact question? Our theory is n to power 4 over -2 to power n plus 1. So let's apply the ratio test. By the ratio test, I'm taking the limit of absolute value of a n plus 1 over a n when n approaches infinity. So we take the limit of an plus 1, it's n plus 1 to power 4, and denominator is negative 2 to power n plus 1. We add 1 to it, so it's n plus 1 plus 1. And an is n to power 4 divided by negative 2 to power n plus 1. You may want to rewrite it as numerator times reciprocal of denominator. Let me do that. So we have n plus 1 to power 4 in the numerator and negative 2 to power n plus 1 in the numerator, and in the denominator we have n to power 4 and negative 2 to power n plus 2. So you may want to write it as absolute value of n plus 1 to power 4, absolute value of negative 2 to power n plus 1, absolute value of n to power 4, and absolute value of negative 2 to power n plus 2. And then, because these two terms in the numerator and denominator have the same exponent, you may want to write it as absolute value of n plus 1 over n to power 4, and the next one is negative 2 in the numerator and denominator to exponent n plus 1, and there is 1 negative 2 in the denominator as well. Why? Because the exponent here is n plus 2, and here I have n plus 1. Okay, this one is 1, and 1 to any exponent is 1. Here I have negative 1/2 in the absolute value, so the answer is just positive 1/2. And then we have n plus 1 divided by n when n approaches infinity. The answer here is 1. 1 to power 4 is just 4. Sorry, it's just 1. So we have 1 and 1 and 1/2. The final answer is 1/2. Again, by using the ratio test, the answer is 1/2. 1/2 is less than 1, this limit, and we conclude that sigma an converges absolutely. The next question is a series of negative 1 to power n plus 1 and exponent n of the fraction 2 plus n divided by 20 plus natural log of n. Because here we have exponent n, it's better to use the root test. So let's apply root test here. By the root test, I'm calculating the limit of root n of absolute value of a n, which is negative 1 to power n plus 1 and 2 plus n divided by 20 plus natural log of n. So let's separate them and write it as absolute value of negative 1 to power n plus 1 and the absolute value of 2 plus n over 20 plus natural log of n when n approaches infinity. Absolute value of negative 1 to any exponent is just positive 1, so the remaining part is limit of absolute value of 2 plus n divided by 20 plus natural log to exponent n. So we have root n and exponent n, so the remaining part is a limit of 2 plus n over 20 plus natural log of n when n approaches infinity. Okay, And now, because all terms are positive, you may want to um, get rid of the absolute value and write it as 2 plus n divided by 20 plus natural log of n when n approaches infinity. Okay, when n approaches infinity, in the numerator you have 2 plus n, and n is greater than 2 because n approaches infinity. So in the numerator you just care about n, and in the denominator you just care about natural log of n because it is much bigger than 20 when n approaches infinity. You know that natural log of infinity is infinity. So in the numerator, to take the limit when n approaches infinity, I have n, and in the denominator I have natural log of n. So what is the answer? Because it is equals to n divided by natural log of n when n approaches infinity. When I was speaking about the limit of sequence, I mentioned there is a rule. Limit of natural log of n divided by n when n approaches infinity is 0. This limit approach 0 because the rate of natural log, the rate that natural log approaches infinity is much less than the rate that n approaches infinity. When n approaches infinity, denominator, which is n, directly goes to infinity. But natural log of n goes to infinity, approaches infinity, but with really smaller rate. So this division and this limit is equals to 0. But right now we have the opposite. The rate that n approaches infinity is really faster the rate that natural log approaches infinity. So this limit it's equals to infinity and does not exist. As you see, I applied root test and the answer is infinity. It is greater than 1. So I conclude that this series sigma of an diverges. That's all about the root and the ratio test. By finishing these two tests, we already know all different tests for checking the convergence or divergence of series. I hope you learned the material and see you in the next video.